First Law of Thermodynamics. Is that the change in internal energy is equal to the heat flow plus the amount of work done. And we should note the sign convention here. Q is the flow into the system, and work is work done on the system. So in other words, in both cases, energy is going into the system. And the first law is really just conservation of energy. Let's go ahead and unpack each of these terms. So let's look at the different aspects of internal energy. And we can look at internal energy, and we should always do this with things in thermodynamics. We should try to look at it from two different viewpoints. The first would be a macroscopic viewpoint. In other words, is there something that we can see or detect anyway that tells us something about the system? And from the macroscopic viewpoint, we'd say that internal energy is just the energy stored in an object. And so, for instance, if we had two copper blocks, and one was hot and one was cold, they're obviously different. And so we would say that the hot block has a higher internal energy. And higher temperature is just one of the ways in which a system could have a higher internal energy. We can also look from the microscopic viewpoint. So if we look at the level of atoms and molecules, is there some difference in an object that has a higher internal energy? What we can do is break down internal energy into a bunch of different buckets or storage mode. So the first one we could say is that there's going to be translational motion. So translational motion, for instance, if we look at the nitrogen molecules in the air in this room, we know that they're flying around, so they're translating, and that's one way of storing energy, right? Each molecule has energy 1/2 mv squares. It has kinetic energy. We also have, those same molecules are also going to be rotating. Okay, so we imagine, if they're polyatomic anyway, that they can rotate, and that's going to store energy. You might remember from rotational physics that each of them will have kinetic energy 1/2 I omega squared. So it depends on the rotational speed and also the moment of inertia of the molecule. We also know that if there's bonds in a molecule, those bonds are going to vibrate, and that's another way of storing energy. Okay. If we have different electronic states, so for instance, some molecules could be in something other than their electronic ground state. If they're in anything higher than their ground state, they're storing energy electronically. And we know that if we have anything other than a perfectly ideal gas, we're going to have intermolecular forces, so I'll just put IMF. And you can store energy by changing the density of a gas, liquid, or solid by stretching out the intermolecular forces by taking molecules farther apart. So those are the different components of internal energy. Now what about work? The fundamental definition of work is that work is equal to the dot product of the force integrated with displacement. And so, because it's a dot product, it's going to be negative if the force and the displacement are in opposite directions. And of course, we can write this in angular motion. There's a similar equation if we're talking about twisting something with a torque through a specific angle. Of course, those are both vectors as well. Now, it turns out that we can apply these two general equations to a bunch of different situations and get new equations for work. And the most important for this course will be the work of surface tension basically this is the work of surface expansion. So if we create a surface where there wasn't one before, and electrical work, where in this case, I'm going to shrink this a little bit here, where we're integrating, in this case, over the potential, in other words, the charge, the voltage. So if we move a certain amount of charge through a certain potential, it takes work to do that. It takes 1 joule if we want to move a charge of 1 coulomb through a potential of 1 volt. Okay, the most important one, though, is expansion work. This is something we're going. Let me just annotate this. That this is electrical work. So let's go on to the next slide for expansion work. Most important form of work for this course is going to be expansion work. And it turns out this is equal to the negative integral of the external pressure to the change in volume of the system. And make sure you understand that this equation is only true for the external pressure. Okay? So otherwise you're going to end up with some answers that are wrong. Important to note for all forms of work is that work is not a state function. In other words, we can't talk about how much work is in something. Work is characteristic of a process, not of a state. Finally, we have heat. And heat, I think, is pretty intuitive. If we imagine we have 2 blocks of some material like copper, and we put them next to one another. Maybe one's at 50 degrees C and the other one's at 100 degrees C. We know what's going to happen. If we allow enough time to pass, we're going to have, let's assume for a second the blocks are the same material and the same mass. We know that we're going to end up with 2 blocks at 75 degrees C. So it must be that there is a flow of energy in the form of heat from the that was a mistake. Let me erase that. The transfer of energy from heat from the hot to the cold. And so the important thing for heat transfer is that it always involves a temperature difference. If there's not a temperature difference, then there cannot be a heat transfer. And the second thing to remember about heat is that it is once again not a state function. And so we cannot talk about an object containing heat or that it has a certain amount of heat. We can only talk about a certain amount of heat being transferred during a process.